So with organic acids, we need to know how to name these acids. And if you remember from Gen Chem 1, remember when the anion ends in "ate," we replace the ending with "ic." And for most organic acids, the anion form of the acid ends in "ate," so we always add the ending "ic" at the end of the acid name. So it's always going to end in "ic," like acetic acid has the acetate ion, which is a very simple organic acid. And so when we're dealing with organic acids, we have to count the number of carbons in the longest chain. And we always start with carbon 1 at the reaction center, which is the carboxylate group. So here at the carboxylate group is where we start with 1. So you always start number 1 at the carboxylate group. That's the first carbon. And then the second carbon, third, fourth, fifth. So there are 5 carbons in this chain, and you notice that all 5 of these carbons have single bonds. So the first part of this name is pentanoic acid. So pent meaning 5 carbons, and meaning single bond, oic meaning acid. And so now we have to take into account this chlorine group, and the chlorine is off of the third carbon, so we just simply write it as 3-chloro pentanoic acid, or you can write it as one word too, since there's only one group. You can say 3-chloro space pentanoic acid, or you can say 3-chloro pentanoic acid as one big word. So that's the name of this acid. Next we go to B, and in B we have a special category of acid which has a carboxylate group attached to a benzene ring. And so whenever you see something like this, where you have a carboxylate group attached directly to the, or I should say one carboxylate group directly attached to the benzene ring, this root word here is called benzoic acid. So anytime you see this group, it's always, that's the root is benzoic acid. And now we have to take into account the group that's also attached to the benzene ring. And so with benzoic acid, you always start carbon 1 with the carbon that has the carboxylic group attached to it. So that's carbon 1, carbon 2, carbon 3, carbon 4, 5, and 6. So you always start with the shortest side to get to your other group. So here the fluorine is on the third carbon, and there are different ways you can write this. I'll tell you the systematic way. So one could be, you could write 3-fluorobenzoic acid. But since it's a benzene ring and it's at the 1 and 3 position, you can write M-fluorobenzoic acid. And it's the same thing. So M means meta. Meta means that there's a group at the 1 and 3 position. And so that's the name of this acid. We go to the third example. So again, we always start the first carbon with the carbon attached to the carboxylate group. So we have 1, 2, 3, 4, 5, 6. And so here the root would be hex because there's 6 carbons. And now since there's a double bond in that carbon chain, we have to use the other root called ene, oic. So hexenoic is the root of this. But we have to indicate after which carbon the double bond comes after. So the correct answer would be 3-hexenoic acid. And you always start with the shortest way to get to the group or multiple bond. So you go 1, 2, 3. The double bonds after the third carbon, so it'd be 3-hexanoic acid. And so that's the names of these 3 acids listed here. Right. So now identifying the strongest acid. So in addition to watching the previous video, Acids Part 2, there's also one that says Guidelines for Acid Strength. Strongly recommend, if you haven't watched that, to watch that as well, because it kind of goes over the criteria on what we use to identify which one is the strongest acid. And just to give you a little bit of an insight, we use the acronym higher, but for acids we go backwards. So we start with the E and then we work our way backwards. So E stands for the element attached to the acidic proton. R stands for resonance. I stands for inductive effect. And H stands for hybridization. So this is kind of the hierarchy that you would use to help evaluate the different organic. This even works for non-inorganic acids as well, too. So we have all three of these acids, and if we look at all three acids, the acidic proton are all connected to an oxygen. So for the element attached to the acidic proton, it's inconclusive because they all have the same element. Now we look at resonance. Well, this acid has resonance because that double bond can flip back and forth. So you can have resonance here. You can have resonance here. And you can have resonance here as well. So that's inconclusive because they all have the same resonance, the same element attached. So now we go to the inductive effects. And with the inductive effect, there are two groups of compounds we talk about. We talk about electron withdrawing groups. These are usually extremely electronegative or electronegative groups. And then we have electron donating. And these are generally like your alkyl groups, like methyl groups, ethyl groups, etc. So what an electron withdrawing group does is it removes electron density from the reaction center, which is the OH bond, making it easier for the hydrogen to be removed. Electron donating groups do the opposite. They pump electron density back into the reaction center, making it harder for the hydrogen to leave, making it a weaker acid. So again, the key principle is the easier it is to pop off that acidic proton, the stronger the acid is. And so now if we look at the inductive effect, we see here that in number 1, we have an electron donating group, that methyl group. So what that methyl group do is it's pumping in a little bit of electron density back into the reaction center. And so what's it going to do is it's going to make that OH bond a little bit more stable, making it just a little bit more difficult for that proton to pop off. Now if we go to the second one, we have chlorine. And chlorine is an electron withdrawing group. And so what chlorine is doing is it's pulling away electron density from the reaction center. Again, it's pulling electron density away from that OH bond. So if you pull electron density away from that OH bond, the H is not as tightly bound to the oxygen, making it easier to remove. And so therefore, and then of course 3 has no electron donating or withdrawing groups. So in this example, number 2 would be the strongest acid listed because it has the electron withdrawing group, whereas in 1 it has an electron donating group. So in this example, we have 3 different acids. Again, we're going to use the higher principle, but backwards, H-I-R-E. So we want to first look at the element attached to the acidic proton. So we have S-O-N. So they all have different elements attached to the acidic proton. So now what we need to do is when comparing elements on the same row, or same period, I should say, we look at electronegativity. So the more electronegative element is the stronger acid. So between OH and NH2, N and O are on the same periodic table or same period. So O is more electronegative. So OH would be have a stronger acidic proton than NH2. Now we got to look between OH and SH. So O and S are in the same group. So when comparing elements in the same group, we look at polarizability. So the more polarizable, the easier it is for that proton to pop off. And so remember, as you go down a group, the more electrons you have, the more polarizability you have. So in this example, the thiol, which is what this is, would be a stronger acid than the OH, because S is more polarizable than O. Again, as you go down a group on a periodic table, the polarizability increases because you add more electrons as you go down a group. So the more electrons you have, the greater polarizability. So now we have, again, 3 acids. We want to identify which one is the strongest acid. And so here again, we're going to use the higher principle, but we're going to go backwards. So the first thing we look at is the element attached to the acidic proton. So here we have an oxygen, and an oxygen. So they all have the same element. Then we go to resonance. And so you see this carboxylate group always has resonance associated with it. So the more resonance you have, the weaker that OH bond is, because what happens is this OH gets divided between 2 positions, so it's a little bit weaker, therefore making it easier for the acidic proton to pop off. So they all have the same elements, they all have the same degree of resonance. Now we got to look at the inductive effect. Well, the first one has a fluorine at the end. The second one has a bromine in the 2 position. And the third one has a fluorine in the 2nd position as well. And so remember, inductive effect, we're looking for electron withdrawing, and I strongly recommend you go back and look at the lecture notes. It gives you a chart of the different types of electron withdrawing groups and which ones are stronger electron withdrawing than others. And so here, one way to determine the strength of electron withdrawing group is to look at electronegativity. And so fluorine is more electronegative than bromine, so fluorine would have a greater ability to withdraw electron density. So we can go ahead and negate number 2, because bromine is less electronegative than fluorine. By the way, if you had a nitro group, which is an NO2 group, that's actually one of the strongest electron withdrawing groups, is a nitro group. It's actually stronger than the fluoro group. So just keep that in mind. Nitro groups are extremely electron withdrawing. It's very strong. So now we have 1 and 3. The only difference is the position of the fluorine atom. And so what we're looking at is the closer the electron withdrawing group is, the greater its electron withdrawing ability is. So that fluorine, if it's closer to the reaction center, can pull more electron density away from the reaction center versus if it's further away from the reaction center. And again, the reaction center is always the OH bond. So the closer you are to the OH bond, the stronger the effect is. So in that case, number 3 is the strongest acid. And again, in all of these types of comparisons, we're comparing mainly apples and apples. If you want to get into the nitty-gritty, you can wait till organic chemistry. But this is just to show you the basics, comparing very simple acids. So now we have 4 acids, or 4 compounds. We want to determine which one is the strongest acid. And so here we kind of shuffle it up a little bit. And you see, first, if we use the higher principle, first the elements, so of course 3 of them, the acidic protons attached to the oxygen, 1 of them is sulfur. Now here, again, if we were comparing very similar structures, you know, the OH and the SH, of course the SH is more acidic than the OH because S is more polarizable than the O. So we can cross that one off. But now we got to look at this SH compared to the carboxylic, or the ones with the carboxylic group. So not only do they have a hydrogen attached to an oxygen, but additionally they have resonance. So again, resonance means that double bond can flip back and forth between the two oxygen positions. So that double bond flips back and forth, whereas SH has no resonance. So the fact that SH has no resonance would mean it's not going to be the strongest acid, because at a hydrogen there's no resonance in the SH group. So now we're down to 1 and 3, and the only difference between 1 and 3 is that 1 has an OH and 1 has an OH2+. So when you're looking at both of these, you got to ask yourself, which one would the hydrogen have an easier time departing from? And the answer is number 3, because this OH2+ is extremely unstable. So it's that one hydrogen is going to very easily pop off versus the one that just has OH. So that OH2+ means that one of those hydrogens is extremely unstable, doesn't take much to pop it off, and therefore it would be the stronger acid. So again, yes, sulfur has the greater polarizability, but there's no resonance in this structure. So again, the ones with resonance have an easier time deprotonating their acidic proton versus the one that just has SH. And the last one is going to be a little challenging one here. But you see, okay, we have HClO, HI, HF, and benzoic acid. By the way, HClO, don't get confused about what the hydrogen is attached to. It's always attached to the oxygen. And then we have HI. And HF. So here, if we look, we see that the acidic proton is attached to an oxygen here, a fluorine here and an iodine here. So we want to know the strongest acid. Well, 1, 2, and 4 have no resonance. Benzoic acid, of course, has resonance. However, even the resonance in this doesn't match the polarizing ability or the electronegativity of F or I. So again, benzoic acid, yes, it has resonance, and yes, the hydrogen is attached to an oxygen. But again, here, HF, F is extremely electronegative. So compared to O and F, the H would be easier to remove from the F because again, it's extremely electronegative. These are in the same period. And so HF would be a stronger acid than, say, HOCl and even possibly benzoic acid. But now HF and HI, I here, as we're going down a group, I is extremely polarizable because it's like the furthest halogen, the normal halogens on a group. So again, as you go down a group, polarizability increases. And also iodine is very large atom. And so what happens is, since this is very polarizable and a very large atom, this hydrogen comes off very easily. And so since this comes off very easily, HI would be the strongest acid. Because again, compared to HF, it's more polarizable. Compared to the ones with oxygen, again, more polarizable. The hydrogen's further away. It's easier for the hydrogen to remove. And so again, with naming or not identifying the strongest acid or the weakest acid is very important to use the higher principle backwards. Now for weak base, for bases actually, we go the opposite way. So we'll talk more about that in another session.